In this lesson, we'll introduce the methodology of optimization, and we'll start with the simplest form, which is known as unconstrained optimization. So we'll talk about this through three problems. So the first one we've seen before, profit maximization, and this is the iWidget problem. And the problem is, given a cost and demand function for a product, find the price that you should set for this product so that it produces a maximum profit. So profit maximization. The second problem is an inventory replenishment policy, and I call this Gears Unlimited. So given an annual demand and cost for both the ordering and holding, calculate the reorder quantity that minimizes the total cost. This is a problem that is used every day and is embedded in most supply chain software solutions, in most ERP, enterprise resource planning models. And so widely used, and we're going to show how it's developed. Third problem. This deals with packaging, and this is a problem I call Boxy.com, and we want to calculate the package dimensions that maximize the total usable volume given a specific set of cardboard sheets. So three very different problems dealing with maximizing profit, minimizing cost for inventory, and then maximizing volume in terms of packaging. So they seem very different, but in fact, they have a lot of very common features. Each of these problems requires the use of a prescriptive model. This, in other words, it's asking, what should you do? What is the recommended solution? It is not a descriptive model. It is not a predictive model. These require prescriptive solutions. So this is kind of a key that it'll probably be an optimization problem. Now we'll utilize a math function to make a decision in each of these problems. Also, each of the problems looks for an extreme point solution, and they are unconstrained in that there's no resource limit. Now I'll explain this and it'll become obvious a little later. So how are we going to do this? We're going to use calculus. But before we do that, let's talk about what an extreme point is. Because when we mention an extreme point of a function, we mean something very specific. Essentially, an extreme point is where the function takes on an extreme value. Seems kind of a cyclical definition, but it really means you're at a minimum or a maximum, an extreme solution. So I'm either the biggest it can be or the smallest it can be. So if I'm maximizing profit, I want to find the highest value, obviously. And if I'm minimizing cost, I want to find the lowest value of that function. The extreme point also is interesting in that it's the point where the slope, or the rate of change, remember slope is just rise over run, of the function is equal to 0. So that's a critical point because we're going to leverage that to identify where that point is. So let's look at extreme points. Again, they'll typically be minimum or maximum. There's also something called an inflection point. I'll show that. It's not as widely used. You won't see it as much. But the minimum and maximum points, these extreme points, can either be global or local, and I'll explain that in a second. But let's look at a function. So I've got x on the horizontal, y on the vertical, and here's my wacky function. Now, does this function look continuous? Yes, I could probably draw this without lifting my pen off the paper. It is continuous over this range of x that we see. Is it convex? No way, right? You look at this, it's certain got all sorts of bumps. So some pieces of it are convex where it would hold water, but as a whole function, it is neither purely convex or purely concave. But let's look at the extreme points. So here, this point on the curve is what's known as the global maximum. Why is it, how do I know that this is a maximum point? Well, think of it as walking up a hill in the dark. How do you know you're at the top of a hill? You take a step, you go up. You keep taking steps until you go up. When you're at the top, if I take a step in any direction, I'm not going to go up anymore. I'll be either level or going down. So that's the same kind of approach here. Whenever I have an extreme, a maximum, my slope will be, increasing, decreasing, then it goes to 0, and then it goes in the other direction. Now, why do I know it's global? Well, I can look at it here, but we'll talk about other tests that we need because it's not always clear if you're at a maximum point, if it's the global one, or if it's just a local condition. So just like we have a maximum, a global maximum, we also have a global minimum. How do I know I'm at a minimum? I'm walking down a valley, and the next step I take, it doesn't go down further, it starts leveling out, or it starts going up. So you can think of it in those sense. So the slope hits 0 at some point, and then it starts going up again. I can also have a local maximum. This is, again, I'm walking up this mountain in the dark. I hit a maximum point. I don't know at that point, if it's at night, if there's another peak further out, but I know I'm at a maximum right there, right? But it's local because it's only in this area, right? If I look at the whole function that I see here, it is not the global maximum because this point up here is higher. And just as I have a local maximum, I can have a local minimum as well. And then you've got this inflection point. It's like a plateau. Again, it's mathematically there. We won't see it too often. So I wouldn't worry about that too much. We're going to be mainly looking for extreme solutions, minimums and maximums. So how do we find these extreme solutions? We're going to use differential calculus to find where the slope of a function is equal to 0. That's it. That's all we're going to do. It's a great technique. And again, it's widely used in that it's embedded in most of the software that you're going to use. Now, we'll be using differential calculus, and somehow the word calculus scares people sometimes, but relax. We're only going to use a little bit of it, and it's really easier than you think. All right, so let's get started with that.